In this section, we're going to take a look at conic sections, in particular, the parabola.
Now, you might think, well, we already know what a parabola is. That's something we've seen since algebra. It's the graph of y equals x squared, or maybe y equals x squared plus 2, or y equals 3x squared. It's the graph of some parabola. That is, it's the graph of some quadratic. That is absolutely correct. However, there are a few things about that view of the parabola that miss some key features of it. So let's go ahead and take a look at the parabola again from the point of view not of it's the graph of y equals x squared, which it is, but from the point of view of a conic section. You'll remember in previous sections we talked about the ellipse as being what happens when you take a cone and you take a slice of it horizontally, that gives you a circle, or almost horizontally, that gives you an ellipse with a different major and minor axis. Now, if you take a cross-section vertically, that gives you a hyperbola with two branches, one facing up or down, or perhaps facing left and right. A parabola is what you get when you have something in between those, not horizontal, not vertical, but off to an angle, maybe 45 degrees. In that case, you'd end up slicing this way. Note that what that does is it does loop around the back of this cone. Now, it doesn't, if you keep following this down, it doesn't actually cross the bottom half of our cone, only the top half. So you don't have two branches like the hyperbola does. But note that it does go off the edge of this cone, which means it doesn't ever loop back and close back around the way you have with an ellipse or a circle. So here you have a single open part that goes up and opens without ever closing back in on itself. That is what you would typically think of when you think of the parabola. Something that looks like this. Just like the circle, the ellipse, and the hyperbola, this is another example of a conic section. A cross-section of a cone, hence conic section. Note that your parabola, unlike the ellipse or the hyperbola, only has one vertex. Likewise, unlike the hyperbola and the ellipse, it will only have one focus, which we'll talk about here in just a moment. And instead of having a second focus, it'll have something else, which we have not seen before, either from either of our previous conic sections or from any previous views of a parabola. Another thing to note here is that our parabola, as we have seen in algebra, can face up or down. So your vertex can be the minimum or the maximum. But also, it can point this way or this way, left or right, in which case your vertex is either the rightmost extreme or the leftmost extreme. Your vertex is your most extreme value, whichever direction it may be in. So let's take a look at a definition of a parabola that is different from the traditional, it's the graph of y equals x squared. It's the graph of a parabola. Not that it isn't, but this is a different view of it with emphasis on some geometry. So a parabola is the set of all points, which we'll call P. Those points are each designated as P, on the plane. On the plane. Again, this may be a three-dimensional cone, but the parabola is flat. It's on the XY plane. That are equidistant from a fixed point. That's our focus. And a fixed line, which is called the directrix. So unlike our previous ellipse or hyperbola, we don't have two foci. We have a single focus and a directrix. A line that is perpendicular to the directrix and passes through the focus is called the axis of symmetry. Where the axis of symmetry and the parabola cross, that's called the vertex. The parabola and axis of symmetry cross at what's called the vertex. As always, a picture is worth 1,000 words. We're going to begin with a point, which we'll call the focus, and a line, which we'll call the directrix. Now, this line doesn't have to be vertical. However, for this first illustration, I will make it vertical. Neither the focus nor the directrix are part of the parabola, but they are instrumental in determining what the parabola is. What we now want to do is we want to find any points that are equidistant from this focus and this directrix. For example, this point right here would be equidistant because, say, for example, if that's 1 inch, then that's also 1 inch. It's halfway in between those. There's lots of other points that do that, though. For example, this point up here. This point, if I measure the distance from the focus to that point, and I call that, for example, D1, and I measure the distance from the point to the line. Now you might say, well, wait a minute, how do you do that? You can go this way, you can go this way, you can go this way. When we say the distance, we mean the shortest possible distance. In other words, right across. So that's D2. Notice this D1 and this D2 are shorter than this D1 and this D2. But that's okay. What we mean is this distance is the same as this distance. If this distance gets longer, then so does this distance. If you find every point that does that, every point where the point is then you form your parabola. All right? So that's not to say the distances are always the same from one point to another. What it means is if you pick a point on that parabola, the distance from that point to the focus and the distance straight across to the directrix are the same. This D1 and this D2 are the same. Using that definition, I suppose I should draw this other stuff here. If you take a line that is perpendicular to your directrix and which passes through your focus, that's called the axis of symmetry of the parabola. The axis of symmetry is exactly what it sounds like. Your parabola will be symmetric about that line. What's above it in this case is the same as what's below it. So here is our axis of symmetry. And the point where your axis of symmetry and your parabola meet, that's your vertex. So now we can use this definition to find the form of the equation for our parabola. Now again, you might say, I know the equation of a parabola, y equals x squared, or maybe x equals y squared if I wanted to go sideways. Well, that may be true. However, that is missing something. It's missing any mention of a focus or a directrix. And since those are apparently instrumental to the definition of a parabola, then shouldn't our equation include those somehow? So that's what we now need to find. We need to find our equation, which we kind of already know, y equals x squared or x equals y squared, but we need to find some way of incorporating these values so that we know where the focus and where the directrix are. So let's go ahead and give that a try. We begin by placing all of this stuff on a coordinate axis. After all, analytic geometry is far simpler than descriptive geometry. Things are easier on a coordinate axis. For the sake of simplicity, I'm going to place my vertex on the origin. You say, well, why does that make it simple? Why don't I want the focus or the directrix at the origin or through the origin? You could. It really doesn't make too much of a difference, but I've done this a few different ways, and really the arithmetic works out the nicest if you put the vertex at the origin. If you put anything else at the origin, you will get the same answer, of course, but it does work out a little simpler if we put the vertex there. So there's my vertex. And for now, I'm going to have a parabola that opens this way, toward the right. Of course, you can have ones that open in any direction like this, which we will, once we have this equation, we'll modify that one to compensate for any of the other orientations. All right. So here is our parabola. We're going to have a focus. Now, note that your focus is along your axis of symmetry, as is your vertex, which means here that is going to be on the x-axis. So as it's on the x-axis, it is some distance away from here. I'm going to call that distance p. So the distance from the vertex to the focus, I'm going to call that p, which means this is the point p comma 0. Okay. Well, remember, if you pick any point on your parabola, the distance from that point to the focus is the same as the distance from that to the directrix. So if this is p units to the right, well then the directrix must be p units to the left. Whatever p is, you're going to have that many units to the left for your directrix. Okay, so that's a vertical line. And if that's 0, 0, you go back p units, that's going to be x is equal to negative p. This is what I meant about making the arithmetic a little easier. P versus negative p. Okay, so now we know where our directrix is and where our focus is. Remember how this works. The distance from your focus to some point on your parabola, if we call that D1, that's going to have to be the exact same as the distance from that point to the directrix, D2. And I didn't do such a great job of that. It doesn't look like these are equal to each other, but again, these are meant to be equal. Here, this is just a sketch. I didn't actually take the time to make sure that it was exactly the right size. But in order for this to actually be a parabola, these would have to be equal to each other. Okay, well, what are these? Well, let's see. This is just some point on my parabola. It's not any special point. It's just any point. So we'll call it by the most generic name we can think of, x comma y. We already know what this is. This is p units to the right of the origin, so p0. Now this point we don't know. Oh, but we can figure it out. After all, this point is on this directrix. The equation of the directrix is x equals negative p. So that means that any point on here has an x value of negative p. Okay, so we know the x value, it's negative p. What about the y value? Well, it's got to be the same as this y value. After all, the shortest distance means you come straight across, which means you keep your y value the same from here to here. So your x value changes, it's to be specifically negative p, but your y value will remain the same. So that means that d1 is going to equal to the square root of, okay, well, take the difference of your x values. That's x minus p, and you're going to square it, x minus p. And then take the difference of your y values, y minus 0, and you're going to square that, and those get added together underneath the square root. Since you have a 0 here, y minus 0 is just y, so you can write that as the square root of x minus p squared plus y squared. On the other hand, d2 is equal to the square root of, well, now that's this one across here. Take the difference in the x values, x minus a minus p, or in other words, x plus p, and that gets squared, plus the difference in the y values, that's y minus y, squared. But here, y minus y is 0, so that whole thing can go away, and you're left with square root of x plus p squared. Okay. Now, by definition, those distances, that d1 and d2, must be the same. By definition, those are this point is equidistant from this point and this line. So, by definition, d1 must equal to d2. So, that means this square root equals that square root. Square root of x minus p squared plus y squared equals square root of x plus p squared. Well, if those two are equal to each other, I could square both sides and they'd still be equal to each other. Oh, but by squaring both sides, that gets rid of my square roots. Thus, x minus p squared plus y squared is equal to x plus p squared. No more square root and no more square root. And so, I can always expand this. X minus p squared, x minus p times x minus p. That's x squared minus 2xp plus p squared. And then don't forget your y squared right there. Is equal to, if I square x plus p, that's x plus p times x plus p. That's x squared plus 2xp plus p squared, like that. Notice that I have an x squared on both sides of that equation, so I can subtract that away from both sides. And I have a p squared on both sides of that equation, so I can subtract away p squared. And so all of those terms disappear. Which gives negative 2xp plus y squared equals 2xp. And now, even though I can't cancel those, I can combine them, because now I can add 2xp and add 2xp over here. That goes away, and that doubles up. Therefore, by isolating y squared, we get y squared equals 4xp. But that looks familiar. After all, we're used to something like x equals y squared. Yeah, that would be a parabola. Y equals x squared. That would be a parabola facing up. X equals y squared. Okay, that's a parabola facing to the right. Okay, so that does look right. But what about these other numbers? 4p. Well, what was p again? Oh, p is that distance from the vertex to the focus and from the vertex back to the directrix. So this looks familiar. It looks like the equation that we've seen since college algebra, but now it's written in such a way to account for this distance so that we can locate these new features, the directrix as well as the focus. Just like with the hyperbola and the ellipse, note that if you subtract some value from x or from y or both, that will change the location of your object. A parabola doesn't have a center. However, we will treat the vertex as the center. So here, notice that when you don't add or subtract anything from the x or y, your vertex goes through 0, 0, through the origin. If you add or subtract something from x or y, that will modify the entire parabola, the focus, the directrix, and everything else. But the easiest way to keep track of it is to see where it takes the vertex. So, a more general form of the standard form of a parabola. Standard form of a parabola is you have y minus k squared equals 4p times x minus h, where h and k are the location of the vertex, and where p is the distance from the vertex to the focus and the directrix. One in one direction, the other in the other direction. All right. Note that here you have a parabola that is facing left or right when your y is the one being squared. So in this situation, your graph will look this way or this way. It depends on the value of p. Right? If p is positive, then your vertex is your focus is to the right of the vertex. So here, if p is positive, then your focus is to the right, which means the parabola opens to the right. On the other hand, if p is negative, then your focus is to the left, which means your parabola opens to the left. So the value of p determines which direction it opens, left or right. Now, what if you want it to open either up or down? Well, then your x is the one that needs to be squared. So you would have something like x minus h squared equals 4p times y minus k, where, again, same thing. hk is the vertex, and p is the distance from the vertex to the focus and the directrix. In this case, if p is positive, then your focus is above the vertex, so the parabola opens up. On the other hand, if p is negative, then your focus is below the vertex, which means the graph opens down. Like that. So note that that means that p doesn't just give you the distance from the vertex to the focus, it also gives you the direction. Positive to the right, positive up, negative to the left, or negative down. All right, so this covers all four possibilities. So now let's take a look at some examples. So for this example, we're going to find the focus, the directrix, and we're going to graph. Our equation is x squared is equal to 8y. Note, first of all, that you're not adding or subtracting anything from your x or your y, so right away that means that your vertex will be at 0, 0. If you had x minus 5 or y minus 2, then that would alter the location of your vertex. But without anything being added or subtracted to the x or to the y, that's going to give you a vertex at the origin. Next, what we want to do is we want to rewrite it so that the variable that's not being squared can be written as 4 times something times the variable. All right? The y is being squared, the x is being squared. Okay, the one that's not being squared, you want it written as 4 times some number times y. Okay, well that y is the one that's not being squared. So you want to write that as 4, that 8 you want to write as 4 times something. Oh, well, clearly that's 4 times 2. So here that's x squared is equal to 4 times 2 times y. Oh, okay, so now we have our vertex, but now we know that p is the number that's being multiplied by 4 to give us the coefficient. In other words, that's the number 2. So this gives us enough to graph our focus, our directrix, and create our graph. We know that our vertex will go through the origin 0, 0. Since x is the one that's being squared, that means you're either going to go up or down. Notice that p is positive, so that means you're going to go up. Your focus is 2 steps above the vertex. So there's my focus. Okay. My directrix is going to be the same distance, but on the opposite side. So instead of being 2 steps above the focus, we're going to go 2 steps below the vertex, rather, and that will give us our directrix. So now we know the location and the equation of our directrix. It's a horizontal line that's 2 steps below the origin. Okay, so that'll be y equals minus 2. We have our focus that's right above the origin, so the x value is still 0, but your y value is now 2, because again, you went up 2 steps, 0, 2. And now you're going to have your parabola. Now, one thing we have not seen is how wide do I open this parabola? I know it's got to open up this way, but is it going to be really, really tall and skinny? Is it going to be really wide? Exactly how wide do I open that up? Well, note right here that from our definition, the distance from our focus to our vertex must be the same as the distance from the vertex to the directrix. Okay, so how does that help us? Well, if we take a look on either side of our focus, how far is it from the focus to the directrix? Well, that's 4 units, yeah? So if I go 4 units to the right, that is also going to give me a point on my parabola. Right? Because after all, the distance from here to here was 4, and the distance from here to here is 4. But I can do the same thing on the other side. Right? After all, the distance from here, from the focus to the directrix is 4 units, 2 units here and 2 more over here. Okay, so then to go from here horizontal to this is, again, that's 4 units. So as long as I go 4 units to the left, that guarantees me a point that is on my parabola. Because after all, if this distance is 4, and this distance is 4, then this point is equidistant from the vertex and the directrix, which by definition must mean that it's on my parabola. So that now tells me how wide I can make my parabola. Incidentally, how wide was that from here all the way across? Well, that was 4, and that was 4. 4 plus 4 is 8. Hey, look, that was that number. That was that 4p. That was not an accident. This right here, this 4p, that's going to give you the distance across the focus parallel to your directrix. I'll say that again. If you make a line that passes through the focus and that is parallel to the directrix, the length of that line is going to be that 4p, in this case that 8. From here all the way across will be 8. Since everything is symmetric down the middle, that's going to be 4 units on either side. If instead of 8 this was 12, well then you'd have 6 units on either side. The distance all the way across through the focus will be that 4p. So this 4p is not just giving you the location of your focus and your directrix, that's your p there, and that's your p there. But also the 4p is giving you distance from here all the way across to here. This imaginary line, a segment that passes through the focus that tells you how wide your parabola is, this is called the lattice rectum. So 4p is the length of the lattice rectum. where again the lattice rectum is not actually part of the graph. However, it is the imaginary line that connects these 2 points across the focus. That little number does a lot. So go ahead and give this a try. You're going to find the focus, the directrix, and then graph y squared equals 16x. Note that we don't ask for the length of the lattice rectum, but you still need that because that's going to be part of creating the graph. So go ahead and give that a try. Pause the video, give yourself whatever time you need, and once you're done, go ahead and unpause the video and we'll go through it together. All right, so here we have y squared equals to 16x, which can also be written as y squared equals 4 times 4x. So here we have 4 times a number times x. 4 times a number times x. So that number, that p, must be 4. So here we have that p is equal to 4. We have y squared. Okay, so since we have y squared, that means we're going to have our focus either left or right of the vertex. But since p is positive, that means we're going to have it to the right. So p is 4, which is positive. So we have this situation where your focus is to the right of the vertex. All right, so now we have enough to start graphing. Okay. Our vertex, notice we haven't subtracted anything from our x or our y, so that means our vertex will pass through the origin. Since it's y squared, that means our focus will either be left or right, and since p is positive, that must mean it's to the right. Since p is equal to 4, that means you're going 4 to the right. 1, 2, 3, 4. All right, so y squared tells you left or right. Positive means it's got to be right, and the number tells you how far to the right. So that's my focus. That's what, 4, 0? That means that our directrix is going to be 4 units in the opposite direction to the left. 1, 2, 3, 4 right here. And that lattice rectum is now a vertical line, which is what, x equals to -4. Before we had y equals, since that was horizontal. Now we have x equals, since that's vertical. All right, so now we have our parabola. It's going to start from here, and it's going to open this way toward the focus. Finally, the lattice rectum tells you the distance from one point on the parabola to another. It's going to be parallel to the directrix, so it's going to be a vertical line straight up and down, and it's going to pass through the focus. That 4p, that 16, gives you the distance all the way across. Remember, parabolas are symmetric, which means that from here you'd have to go half of 16 up and half of 16 down. So you're going to go up 8 steps, 1, 2, 3, 4, 5, 6, 7, 8, and down 1, 2, 3, 4, 5, 6, 7, 8 as well. So that is our lattice rectum. Again, notice that line is not actually part of your graph. It's an imaginary line from one point on your parabola to another. However, it is still instrumental in finding the size of our parabola. So our parabola will cross through the origin at its vertex and through the points on either side of this lattice rectum. And that is our graph, our focus, and our directrix. Okay. All right, for our next example, let's consider one which is not necessarily in this nice form. What happens when, like we saw with an ellipse or a hyperbola, what if it's not in the standard form? Our standard form for a parabola is either y minus k squared equals 4p times x minus h, or x minus h squared equals 4p times y minus k. But what happens when you have something a little more spread out? Well, there's no surprise here. Just like what we did with hyperbolas and ellipses, we're going to have to complete the square. So for example, here we're going to, let's see here. Yeah, here we're going to find the vertex, the focus, the directrix, and graph. And we're going to have x squared plus 6x plus 8y plus 1 equals to 0. That is definitely not in the standard form, but we can place it in the standard form by completing our squares. To complete our squares, let's begin by having our whatever has a square on it and any other term that has that same variable on one side, everything else to the other. So here, x has a square on it, so we're going to keep this on the left. 6x doesn't have a square on it, but it shares the variable that x squared has. So we're going to leave those two there. Everything else moves over the other way. So we're going to write this as x squared plus 6x equals, moving this over to the other side, that's going to be negative 8y minus 1. Next, we're going to complete the square here. If there was any number right here, of course, we would first factor it out, but there is no number here, so we can simply complete the square on this part here. We're going to take half of the linear coefficient, half of the number in front of x, that's half of 6 is 3, and then square it, which gives you 9. So now this is a perfect square, but notice by adding 9, this is no longer the same equation. Okay, so that's a new number. Okay, well, whenever I add a new number on one side, I have to do the same thing on the other side. So now this will give us a perfect square, which can be factored down as x plus 3 times x plus 3, or more simply, x plus 3 squared, is equal to negative 8y, and then put these together, that's going to give us a minus 8. Oh, no, it's not. It's going to give us a plus 8. That's going to be 9 minus 1 is 8. Notice that this is supposed to be 4 times p times y, either plus or minus a number. Okay, well, that's not quite what this is. Oh, but it can be if we factor out. All I have to do is factor out that first number. I can factor out a negative 8 from these terms, which will give me x plus 3 squared is equal to negative 8 times y minus 1. After all, negative 8 times y is negative 8y. Negative 8 times negative 1 is positive 8. But of course here, this negative 8 can be written as 4 times negative 2. So x plus 3 squared equals to 4 times negative 2 times y minus 1. And now that's the standard form with everything we need. Notice we've subtracted a negative 3 from x, and we've subtracted a 1 from y. So negative 3, 1 is our center. Or you could also say, where do I plug into these parts to make them 0? I would plug in a negative 3 for x and a 1 for y to make them 0. Here, 4 times p times y minus k, oh, then p must equal to negative 2, which is less than 0. Okay, so that should give us everything we need to create our graph. All right, we're going to start out with our center of negative 3, comma 1. So 3 to the left and up by 1, just like that. Okay. Oh, sorry, that shouldn't be a center. This should be the vertex. Yes. The center is what we would call it if we were dealing with a hyperbola or an ellipse. But for a parabola, we don't really have a center. We have a vertex. Okay, so that's our vertex. Notice that the x is the one that's being squared, which means your parabola will either face up or down. And since p is negative, well, that means it's going to face down. So our parabola will face down. Since p is -2, that means you're going to take 2 steps in either direction to get to your vertex and to get to your focus and to get to your directrix. So since that's a -2, that means our parabola opens down, and so that's going to be 2 steps down to get to the focus. What's that? 3, -1? Oh, sorry, -3, -1. That's our focus. Our directrix, if our focus is 2 steps down from our vertex, our directrix must be 2 steps up. So that's going to be a horizontal line, y equals 1, 2, 3. So that is our directrix, y equals to 3. And now we simply need to find the just how wide this opens up. Here we're going to have 4 times our -2. That was our 4p. So that means we're going to have 8 units all the way across. You might say, well, that's -8, isn't it? Well, yes, but you can't have a negative distance. So here, the negative just tells you which direction you are, your parabola is moving in. It's going to open downwards. Aside from that, the negative doesn't do anything. So here, even though that's a -8, you consider 8 as being the distance. Right? So here, we're going to have a lattice rectum that is 8 units across, meaning 4 on either side. So here you're going to go 1, 2, 3, 4 to the left, and 1, 2, 3, 4 to the right. Again, those 2 points are not on our, this lattice rectum is not on our graph. However, the 2 points on either end are, and they tell us just how far open this parabola opens up, or in this case, opens down. So we have our parabola that has a vertex at -3, 1, a focus 2 steps below that at -3, -1, and it opens downward so that at the same level as your I'm sorry, I've made a mistake here, haven't I? I graphed this, sorry, this point is not the vertex. This is the vertex. So I graphed this incorrectly. Here, let me do that again, just this part right here. All of my numbers were right, but I graphed it too high. That point is on my lattice rectum. I'm supposed to be using this point, which is my vertex. So let me graph that again. All of this is fine. I just graphed it too high. All right, let's try that again. We have a vertex of -3, +1, right there. We have a focus that is 2 steps down. Since that's x squared, it opens either up or down, and because that's a negative, that's going to open down. So our focus will be 2 steps below that. So our focus will be -3, -1. And if that's our vertex, that's our focus, 2 steps down, our directrix must be 2 steps up. Looks like that. So now our lattice rectum is 8 units across. Again, the negative doesn't do anything other than tell you which direction it opens in. So here, that -8, you just think of it as 8 units. And so it's going to, the lattice rectum will be a line that is parallel to the directrix. In other words, it's horizontal, and it's 8 units across, crossing through the focus. Okay, well, if it's 8 units across, that means it's 4 units on either side. So it's going to go to the right, 1, 2, 3, 4 units, and to the left, 1, 2, 3, 4 units. So those 2 points are going to be on our parabola. The lattice rectum is not, but it is an imaginary line that connects those 2 points. And so now, starting from our vertex, not from our directrix like I accidentally did before, I started too high. Starting from our vertex, we're going to cross through either end of our lattice rectum. It's going to open in the direction of the focus, and this gives us our graph. So the graph of x squared plus 6x plus 8y plus 1 equals 0 is the graph of this parabola right here that has this focus, and the directrix y equals to positive 3. And that's our result. So I think go ahead and give this a try. You're going to begin by having to complete the square, and then once you're done, you can use that information to create your graph. So go ahead and give this a try. Go ahead and find the vertex, the focus, the directrix, and then graph. X squared minus 2x minus 4y plus 9 equals to 0. Go ahead and pause the video, give yourself the time that you need, and once you are done, you can go ahead and unpause the video and we can go through it together. All right, so we're going to begin by completing the square. Whatever has the square on it and anything else that shares the variable will stay on the left. Everything else moves to the right. So that will be x squared minus 2x will stay there. And then the negative 4y will move over as a plus 4y. And the plus 9 will move over as a minus 9. We're going to now complete the square. We're going to take the, there's no leading coefficient to factor out, so we don't worry about that. We're going to take this number, half, and then square. Half of negative 2 is negative 1. And if you square negative 1, you get a positive 1. And since that's a new number, whatever you add to one side, you do the same thing on the other side. On the left side, you can now factor this. This factors is x minus 2 times another x minus 2, x minus 1 and x minus 1, which is just x minus 1 squared. And on this side, these two combine to give you 4y minus 9 plus 1 would give us minus 8. Notice here we can factor out this 4. Just like up here we factored out this negative 8 to get the y minus something. Here we can factor out the 4 to get the y minus something. So this gives us x minus 1 squared is equal to 4 times y minus 2. Okay, so you're subtracting 1 from the x and 2 from the y, so that gives you your center, 1 comma 2. Here this 4 can be thought of as 4 times 1. Okay, so then p must equal to 1. All right, you can write 4 as 4 times 1. So 4 times 1, that 1 must be your p, which is positive. And since the x is being squared, you know that your parabola is either going to open up or down. Because that's a positive, that means it will open up. So now we have all of the information that we need to create this graph. We begin with our, and I've done it again, it's not called the center here. When it comes to a parabola, that's called the vertex. we don't really have a center for a parabola. So our vertex will be at the point 1, 2. We know that because the x is the one being squared, we're either going to open up or down. And since p is positive, that means we're going to open up. Not only that, but we know that since p is equal to 1, that in the direction you're going to open, you're going to take one step to find your focus. So right here, that is your vertex at 1, 2. So your vertex must be one higher than that at 1, 3. And that means that our directrix must be one step behind that. If one step up is your focus, then one step down as your directrix. So it's a horizontal line, y equals, and it's still one step above the origin. So this will be y equals to 1. All right, so now we're going to have, from this point, it's going to open up toward the focus. But now we need to know how wide it's going to be. Remember, this 4p is going to give you the distance of the lattice rectum, which passes through the focus. Here, 4p is 4, so the lattice rectum will be 4 units across, or in other words, 2 units on either side. So from here, we can go 2 steps to the right and 2 steps to the left. This would be the point, 3, 3. And here, taking 2 steps to the left, that would give us -1, 3. Both of those are going to be points on our parabola. Again, our lattice rectum is not part of our graph. However, it is the imaginary line that connects those 2 points that are on our parabola. And so now we can put all that together. Our parabola will have this lattice rectum. We'll have this directrix, this lattice rectum, and this focus. And it will start at the vertex and cross through the 2 endpoints of the lattice rectum. And that gives us our graph. So we find everything we need. Our vertex is at 1, 2. Our focus is at 1, 3. Our directrix is at y equals 1. And we form our graph that way. All right. Now, of course, we can go backwards. We can start off with some features either given in a graph or just written out, and we can create an equation that satisfies those conditions. So here is an example. Let's find the standard form of the parabola. That has a vertex which has a focus at 2, 4 and a directrix at x equals -4. As with the ellipse and the hyperbola, it is often useful to start with a simple illustration. Sometimes the information is given to you as a graph in the first place. However, if it's not, it's often useful to begin by making your own rudimentary drawing with some key features on it. All right, so here we have something that has a focus at 2, 4. Okay, so that'll be 2 units to the right and 4 units up. And we'd have a directrix at x equals -4. So the directrix would be down here, 1, 2, 3, 4 units below. Actually, no, it wouldn't. It's x equals -4. So that means that we would have a vertical line, 1, 2, 3, 4 units to the left of the origin. So we have a focus 2, 4. Our directrix x equals, that would make that a vertical line, x equals to -4. Okay, that's this line here. All right, well, we know that our line or axis of symmetry is a line that's perpendicular to this axis and which crosses through this focus. Okay. So that's this line right here. And we know that our vertex will lay on the axis of symmetry halfway between the directrix and the focus. So halfway between here and here. Okay, well, that is going to be a point, let's see, how many steps is that from here to here? That's 6 steps. 1, 2, 3, 4, 5, 6. So half of that would be 3. 1, 2, 3. So that would be our vertex. Okay, so what is that point? That's the point -1, and then up 1, 2, 3, 4. Our vertex is -1, 4. So that is the point that is halfway in between the focus and the directrix. Well, that means that we know that our parabola is going to open to the right like this, because after all, that's the vertex, and it's got to open toward the focus. So we know that our equation has to be of the form y minus k squared is equal to 4p times x minus h. All right, the x squared would mean it opens either up or down. The y squared means it opens either right or left. All right, so since it opens to the right, we know it has to be in this form. We now know our vertex, -1, 4, so that will give us the h and the k. So right here, that h is -1, so minus a minus, that'll be a plus. And our k is a +4, so minus a +4, that's -4. And then p gives you the distance from the vertex to the focus or to the directrix. In this case, that's 1, 2, 3 steps. Note that because it is to the right of the vertex, the focus is to the right of the vertex, that p will be a positive value. So that would be a +3. So in the end, our equation will be y minus 4, the 4 being this 4 right here, from our vertex, is equal to 4 times 3, 4 being from the standard form of a parabola, 3 being the distance from the vertex to the focus, and it's positive because the focus is to the right. 4 times 3, that makes 12, times x minus a -1. That -1 being the x-coordinate of the vertex, and minus a minus makes that a +1. And there we go. This is the standard form. At this point, if you wanted to, you could, of course, multiply this out, distribute the 12, combine terms, things like that, but that would not be the standard form. There are other ways to write parabolas and hyperbolas and ellipses, but this would be the standard form of the parabola. So there we go. Go ahead and give that a try. Same question. Go ahead and find the standard form of the parabola that has a focus with focus 7, -2 and directrix 5, -2. And vertex 5, -2. Okay, so your focus 7, -2, your vertex 5, -2, 7, -2, 5, -2. Go ahead and give that a try. It may help if you start off with the sketch, although it's not absolutely necessary, but it does often help to organize your thoughts. In any event, go ahead and pause the video, give yourself the time you need, and once you have the results, once you have an equation for your parabola, go ahead and unpause and we'll confirm that together. All right, as always, I'm going to begin with a simple sketch. My focus is at 7, negative 2. I'm going to go to the right. 1, 2, 3, 4, 5, 6, 7. And then I'm going to go down by 2. And then my vertex is going to be at 5, negative 2. Okay, so 5 to the right, down by 2. All right, so I know that my parabola will open to the right like this, because from the vertex, your parabola has to open toward the focus. All right. Okay, so right off the bat, I already know what form my parabola will take. It'll take the form y minus k squared equals 4p times x minus h. The reason for that, our y being squared tells us you either open left or right. And here it definitely opens to the right. Okay, we actually know everything we need. We don't even need to graph anything else or figure anything else out. As long as we know what we're looking for, we have everything we need right here. After all, this is our vertex, and that's going to give us our h and our k. Oh, but we know what that is. It's 5 and negative 2. So this would be 5 minus our k, which is negative 2, squared, equals 4p times x minus our h, which again is the x value of our vertex. So there's our k and there's our h. P is simply the distance from the vertex to the focus or from the vertex back to the directrix. But we have both of those. The distance between this point and that point are 2 steps. 1, 2. So here P must equal to 2. And so our result is going to be double negative makes that a positive. Y plus 2 squared equals 8 times x minus 5. And that is our result. Taking a moment to step away from the algebra and from the geometry here, let's consider one property of a parabola. This is a somewhat interesting application of a parabola. If you have a parabola and you have its focus. Now let's say this isn't an equation and a point on a plane. Let's say this is a physical object, say for example a metallic dish. And here this object is something physical, for example a light bulb, something that shoots out light. Well, an interesting property of a parabola is that if you have something that is emitting information from the focus, here the information will be beams of light. Of course, a light bulb will send light in every direction. Well, a lot of the light that it sends, in fact half of it, will be back toward this dish. This way, or this way, or this way, or this way. An interesting result, however, is that as long as this dish is in fact a parabola, and so long as this point is the focus of that parabola, no matter which way the light is going, as long as it actually hits that parabolic surface, all of those beams will be shot out parallel to each other. Like that. This is one application of this is a spotlight. You have a big parabolic mirror and you have a light bulb right here, a nice bright light bulb. Turn it on, it'll shoot light in that direction. Another application of that, however, is, at least in my opinion, extremely interesting, and that's you can reverse that. If you have things coming in from this direction, they will bounce off the beam and hit the focus. And you say, well, what possible application could that have? It actually has a very important medical application. Let's say you have a stone in your body, a kidney stone or gallstone, some kind of calcium buildup in your body, something that cannot easily be or safely be surgically removed. One option is we can sit you inside of a parabolic dish. Literally, you can sit inside of here. And we have to be very careful. We have to measure everything very carefully. But we need to make sure that the kidney stone or the gallbladder stone or whatever calcium deposit we're trying to eradicate, we need to make sure that it's right on the focus. And we need to be very precise because the focus is in fact a single point. It's not a spot the size of of a room or the size, a spot of a desk. It's actually a single tiny little spot. But a tiny little spot is really all we need. So we got to be careful. We got to imagine, that is inside of a kidney. And this is my best attempt of drawing a kidney. And of course, that kidney's inside of a person. So, this person's sitting in here, right? Okay, well, now we're going to go ahead and shoot something in here. What we're going to shoot in is we're going to shoot in sound waves. We're going to shoot in very high intensity, high frequency sound waves. They're not something that you can audibly hear, at least nothing more than maybe a light buzz. But what's going to happen is as you shoot that sound in here, it doesn't matter where it hits. Now, of course, some of them will hit the stone directly, but most of them will not. But that's okay, because as long as this really is a parabolic dish, and as long as this really is the point at the focus, what will happen is this and this and this will all be redirected directly to the focus. And so if you just sit the person in there long enough, you shoot in high intensity, high frequency sound waves, and they will bounce and vibrate that stone until they disintegrate it. It'll turn to dust, or hopefully even smaller than dust. And then that can either be filtered out by your body or passed. This is a bit more high-tech, and it's an option that we've had in more recent years, which is certainly a lot safer and a lot more effective than trying to cut something open. And it's certainly a lot less painful than trying to let it pass in a more traditional sense. So this is just a quick application of a parabola. There are applications of ellipses and hyperbolas as well. This is not a class in application. This is a class in preparation for a calculus course. The only application we have is make sure that you understand what's necessary to learn calculus. However, this one was just too interesting for me to pass up. If you have a parabolic dish, if you emit something from that focus, it will shoot parallel to that lattice rectum. If you shoot something in parallel to that lattice rectum, it will focus it to the focus of the parabola. All right, finally, the last couple of things here. One, we have seen conic sections. We've seen 4 of them. We've seen a circle, which really is just a special form of the ellipse. We've seen the hyperbola. And now we have seen the parabola. It turns out that all of these, they're all related because, of course, geometrically, they're all the cross sections of a cone, hence the phrase conic section, right? A cross section of a cone, a conic section. But not only are they related geometrically, they're related in terms of the way their equations are written. The general form of a conic we've seen several standard forms of conics. Y minus k squared equals 4p times x minus h. Or x squared over a squared plus y squared over b squared equals 1. Or x minus h squared over a squared minus y minus k squared over b squared equals 1. We've seen standard forms of conics. It turns out that all of the standard forms can be rewritten to look exactly the same, what's called the general form of a conic. The general form of a conic is as follows. We're going to have ax squared plus cy. You might notice I left a blank there. There's actually a term that we're going to put in our next section, but it's not something that we are quite yet ready to talk about now. Right now we're still talking about more basic forms of the conics. So here ax squared plus cy squared plus dx plus ey plus f is equal to 0. Here, this extra term we'll talk about in our next section. It accounts for rotations. So far, every ellipse we've seen has either had a major axis that's horizontal or vertical. Every hyperbola we've seen has had a transverse axis that's horizontal or vertical. Every parabola we've seen has had a directrix and a latus rectum that's horizontal or vertical. What if it's tilted at 30 degrees? What if it's tilted at 6 degrees? What if it's tilted 89 degrees? Well, that's what that last term will account for, but we'll see that in our next section. For now, we're still sticking with ones that have the some feature either vertical or horizontal, whether it be the latus rectum, the major axis, or the transverse axis. But even without the rotations, here, this is a bit more expansive than any form we've seen so far, and it covers all of these. So how do I know which one I have? Well, it has to do with the relationships of the constants. In fact, in particular, it's these two right here. Okay? So first of all, we want to make sure that the conic section, we need to have A and C not both be 0. If one of them is 0, okay, well that looks a lot like a parabola, because only your y is being squared. If this one is 0, oh well then that's fine, because you still have a parabola. It's your x that's being squared. But if they're both 0, you don't have any squares, and that's just a linear equation. And linear equations are not conics that we're going to be considering. Technically, a linear equation is what's called a degenerate conic. A degenerate conic is something like this. It is technically a conic, but it's not one that we usually consider. The reason it is a conic is you can take this cone and cut it in such a way that you end up with a line. The way you do that is you simply slice right alongside the edge right here. So you don't slice vertically or at a slight angle or off the side, but literally just right down the edge. And if you slice right through here, you simply get a single straight line all the way down the edge. If you slice across this way, you would get a circle. However, if you slice right across at the point where these two meet, well, you're not even getting a circle. Now you're just getting a point. So these are called degenerate conics. Where you technically have a conic, I guess, but not really. It's not what we would normally consider a conic. It's not a circle, ellipse, parabola, or hyperbola. The degenerate conics are the line, which again, that would happen if A and C are both 0, or the point, which would be if everything was 0, right? If everything was 0, 0 equals 0. Yeah. You would have the point at the origin. Oh, I suppose there is a third degenerate conic. If you slice right up and down, that's a hyperbola. But if you slice right along the middle, what will happen is you'll simply get the leading edges of your parabola. So you'll have like a straight line, but you'll have it from both sides of your cone. So what you'll end up with are two lines that cross each other. So you'll have a line if you cut across diagonally. You'll have a point if you cut right at this intersection. Or you'll have two lines that intersect, that cross, if you cut straight up and down like this, along right through the center point. Basically, you get a degenerate conic if you have any line that's cutting through this point. You notice that if you cut up here, over here, along here, that's fine. But basically, if you cut for a ellipse, for a parabola, or for a hyperbola, horizontally, diagonally, or vertically, but you do it through the point in the middle, that gives you your degenerate conic. So as long as you don't have degenerate conics, as long as you don't have one of those, your other conics, or the ones that we usually consider, look like this. And which conic we have depends on the relationship between these numbers, in particular the A and the C. If A and C are equal to each other, then you have a circle. because if these two are equal to each other, when you complete the square, you'll be able to divide out by a common factor, and you'll have x squared plus y squared over r squared. Or you can multiply the r squared over this way. So if a and c are exactly equal to each other, that's a circle. Now, if they're not equal to each other, then, well, there's a few possibilities. The first one is they're not equal to each other, but their product is positive. Then, if they're not equal to each other, but their product is positive, you end up with an ellipse. However, if they are not equal to each other and you end up with a negative, then you have a hyperbola. Finally, if your a times your c is equal to 0, then you have a parabola. Here with the general form of a conic, again, you begin by assuming that a and c are not both 0. Because if they're both 0, then you're going to end up with some degenerate form, either line, point, or 2 points that cross. And I misspelled the word cross. I'm kind of impressed about that one. I think you should be impressed too. I misspelled the word cross. 2 lines that cross. So here, the general form of a conic. Here we assume a and c are not both 0. Assume a and c are not both 0. Then if a and c are equal to each other, you have a circle. If they're not equal to each other, if their product is greater than 0, you have an ellipse. If their product is less than 0, you have a hyperbola. And if their product is equal to 0, you have a parabola. So, for example, let's identify an equation as a type of conic. And when we say conic, again, we're assuming it's not a degenerate conic, not a line or a point. Okay, so let's say, for example, we have y squared minus 4x minus 4y equals to 0. Okay, well, in that case, you notice that remember, your a is the number in front of your x squared, your c is the number in front of your y squared. Okay, so here, there is no x squared, so that means a is equal to 0. And there is a y squared, the number in front of that is the number 1, so b equals 1. Okay, so, all right, let's compare. What are the possibilities? Are a and c equal to each other? C is equal to 1, not b. C is the number in front of your y squared. Okay, all right, so now let's compare. Are a and c equal to each other? No, they're not. Okay, so it's not a circle. Okay, so it's got to be one of the other 3. All right, if you multiply them together, do you get something greater than 0? 0 times 1 is not greater than 0. Do you get something less than 0? No, 0 times 1 is not less than 0. Oh, then the other only option is you get 0. Which, yeah, 0 times 1, a times c, that's equal to 0. So, since AC equals to 0, we have a parabola. This will come in handy in the next section when we start talking about rotations, or when we start talking about, rotations, tilting things back and forth, because it is often useful to know what kind of parabola, hyperbola, ellipse, or circle we have. It's often useful to know what kind of conic we have before we even start. Let's try another one here. Let's go ahead and identify the equation. as a type of conic. Oh, let's see. Let's try 9x squared. 9x squared plus 4y squared minus 36x plus 8y plus 31 equals to 0. Again, all of these other things will tell you things about the center. They'll tell you things about the either the latus rectum in the case of a parabola, the major and minor axis in the case of an ellipse, or the transverse axis in the case of a hyperbola. But the only things that you need to identify what kind of conic you have are these two. So here are a, the number in front of the x squared, that's 9, and our c, the number in front of the y squared, that's 4. Okay, so again, first, if our a and our c are equal to each other, then you have a circle. Okay, well, we definitely don't have that. Okay, so then it's got to be one of the other three. They're not equal to each other. Okay? If you multiply a and c, do you get something greater than 0? Yeah, 9 times 4, that's 36. Ah, okay, so they're not equal, but their product is positive. So that's going to be an ellipse. Since a is not equal to c, and a times c is greater than 0, we have an ellipse. So for our last problem here, go ahead and give this a try. Go ahead and identify the equation as a type of conic. Let's see, go ahead and try 100x squared minus 7y squared plus 90y minus 368 equals to 0. Notice one thing you could always do is you could complete the square, and when you're done, you'd end up with the standard form of either a circle, an ellipse, a parabola, or a hyperbola. But this saves you from having to do all of that. Right here, with just this test, we can figure out what kind of conic we have without having to go through all the algebra of completing the square. So go ahead and give that a try. Pause the video and go through that. And once you have identified the conic, go ahead and unpause and we'll go through it together. All right, here our a, the number in front of your x squared, that's 100. And your c, the number in front of the y squared, is a negative 7. All right, so here, is our a and our c equal to each other? No, they're not equal to each other. Okay, well, they're not equal to each other, so it's got to be one of the other three. Their product, is their product positive? A positive times a negative is a negative. No, that's not it. It's got to be this third one then. They're not equal to each other, but their product, a positive times a negative, is a negative. That means this conic classifies as a hyperbola. So, since a is not equal to c, and a times c is negative, that's what this is right here, negative 700, that means that this fits the criteria for a hyperbola. So we have a hyperbola. And that makes us happy. All right, so that is it. That brings us to the end of this topic and the end of this section. If anyone has any questions, please make a note of those, reach out, and I hope everyone has a nice day.